Okay, so hello everyone. Today we're going to start the more advanced part of the course and actually do special topics and talk about a new paper every session. The material from this point on will not be part of the exam. So the exam covers everything until last session. And I will keep recording the videos for these special topic sessions, but some of these sessions will be presented by other students and we will not record those, both because of privacy reasons and because I don't want them to feel any extra stress. Okay, so with that being said, today we're going to talk about ranking functions. Ultimately, what I want to cover is this paper. But actually, most of the time today will be spent on the background and what you need to know before even starting with this paper. So let me share the visualizer with you and actually start working there. Okay. The chat works. Make sure that everyone can see everything. So this is the visualizer, that's the chat box. Okay. So the problem that we're going to focus on today is the problem of termination. So very informally speaking, what termination means is that you are given some program and you want to figure out whether this program terminates or whether it goes into an infinite loop and runs forever. So another name for termination is halting. And this was a problem that was actually first considered by Turing. And if you've taken theory of computation courses, I'm sure you know that this problem is undecidable. But I'm going to cover this anyway. So the problem is given a program P, and by program I mean any program. So P, you can think of it as a Turing machine, or you can think of it as a C++ program. So given a program P and some inputs, so an input string, let's call it sigma, which is in the alphabet. Decide whether when we run P with input sigma, it terminates. So the first question is, what kind of program is P? So is P deterministic or non-deterministic? Does it have probabilities in it, stuff like that. So let's start with the simplest case and let's just say that P is deterministic. And let's also assume that P is just a Turing machine or any other program. So if P is deterministic, then when I fix some input sigma, then P of sigma is basically just one run of the program. So we are talking about a single execution, and what we're asking is this single execution finite or infinite? Right? And actually, the problem was shown to be undecidable by Turing. So the problem is undecidable. What do we mean when we say it's undecidable? So the formal definition is that there is no program that can get these inputs and create the output that we want. So when we say it's undecidable, we basically mean that no program can do it. So we don't care about the running time. The only thing that we care about the running time of the decision procedure is that it should terminate. So Of course, if I don't want to have termination in my verification, I can just say that have a program that simulates the input and runs until the input terminates. And if the input terminated, it says, okay, this terminates, otherwise it keeps running it. So we don't really look into these kinds of problems. And to be more exact, for a problem, for a verification problem, let's say to be decidable, there should be some algorithm. So let me write it like this. A problem X is decidable if there is an algorithm or a Turing machine, an algorithm A, such that, well, first of all, A is sound. What does this mean? This means that if the algorithm says the answer is yes, then the answer should actually be yes. So this means that if A of sigma is 1, then I should have X of sigma also 1, or sigma in X. If I think of X as a decision problem or as a language. But it also, in our case, it means that if our algorithm says that the program terminates, then the program should actually terminate. Okay. Then we also need completeness. And this is the exact opposite. So it's that if the program terminates, then our algorithm should say that the program terminates. Or if we just talk about an arbitrary problem X instead of just termination, it's that some input is in the language X, then this would give us 1, right? And of course, we expect the output of the algorithm A to be only 0 and 1, we're assuming that. But the third condition that we want for our algorithm is that we want it to actually terminate. A terminates in finite time over every unit. Okay. So whenever in the future I say I have a sound algorithm for some problem, what I mean is that when my algorithm says the property is there, the property is actually there. And whenever I say the algorithm is complete, I mean that whenever the property is there, the algorithm would find it. And of course, we want our algorithm to terminate. And when we say, and when we have such an algorithm, we say that the problem is decidable. So when we said that the problem of halting is undecidable, what that means is that we cannot have an algorithm that is sound, complete, and also terminated. So let's see what happens if we relax some of these. So first of all, what happens if I say, I don't care about soundness. I just want an algorithm that is complete and terminates. Can you give me an algorithm for deciding termination that is complete and terminates, so the algorithm itself terminates? Well, you can just have the obvious algorithm that just outputs 1. Yes. So if my algorithm always outputs 1, then it's complete according to this definition, and of course it terminates. Conversely, if my algorithm always outputs 0, then it's sound, right? Or if my algorithm just never terminates, it's also sound. So sometimes people define soundness a little bit more strictly. They define it to say that if the algorithm returns 1, then the answer should be 1. And if the algorithm returns 0, then the answer should be 0. But I don't want to do that because I really want to capture the second part in completeness. Okay, and what if I want to relax termination? Well, if I relax termination, I can, again, just have an algorithm that simulates the original program. And if it terminates, it says, okay, it terminates. And if it doesn't terminate, then my algorithm will keep simulating it and will not terminate it. So it's really important to have all three of these. And now let me show you the proof of Turing of for why this whole thing is not possible. So why halting is undecidable. So some of you might have seen this before, undecidability of halting. So I'm just going to give a proof sketch. So let's say that there is some algorithm or some program that can actually decide halting. So let's say that, assume there is a program, let's call it F. And let's say that F decides halting. So what does this mean? This means that F of P sigma is 1 if and only if P sigma terminates. And it also means that F itself always terminates. Okay. So having this F, I would create some other program. So let's call this program G. Okay. And what G does is that it just takes as input a single program P. Okay. And then it does this. It says if F of PP, then just loop forever. So while true, else return, let's return 0. Okay, we can talk about that. Okay. So what does this mean? This means that it basically asks about what happens when P is run with the code of P with P itself as its input. Okay, and then passes that to our program F, which decided halting. So this if will hold if and only if when we run P on itself, the whole thing terminates. Right? Okay, now how is G constructed? The way that G constructed is that if this thing holds, then it goes into an infinite loop. And if it doesn't hold, it terminates. Right? So in other words, G of P terminates if and only if P of P does not terminate. Right? Okay, and then the contradiction is what happens to G of G. So does G of G terminate if I give G as an input to itself? Would it terminate? So according to this sentence here, we're basically just plugging in G in place of P. So G of G should terminate if and only if it does not terminate. And that's a contradiction. So this contradiction basically shows that it's not possible to have some program F that decides halting, because if we have F, then we can create this G. Right? Okay, but let's just go back for a second and see where we used each one of these three properties. So when did I use soundness and completeness? Well, I used it when I said this. Basically, I was assuming that F is sound and complete and counting on its answer here, right? So I used soundness and completeness. But when did I use the termination of F? Well, again, if F does not terminate, if this part does not terminate, then the whole program will not terminate. But I'm assuming that this part terminates, right? Because I'm just looking at what happens in then and what happens in else. So I'm also using the assumption of termination of F. Okay, so I hope these have been easy until this point. So now let's see our situation. Basically, the situation is that we have this really important problem of halting, and we need it for a lot of different things. So you will see soon that in many other special topics that we will cover, we assume that the program terminates, and many of the verification algorithms actually do not work if the program does not terminate. But at the same time, we saw undecidability. So we cannot have an algorithm that is both sound, complete, and terminating. Now, we also saw that we can't really compromise on these issues so easily, because if we compromise on soundness or completeness, we get really nonsensical algorithms. And if we compromise on termination, we really don't get anything. Our verification algorithm might not give us an answer at all. So the question is, how can we find a compromise? So there should be at least some family of programs for which we can prove termination, right? And that's actually the problem that we have to look into. So the undecidability result that I just gave you holds for Turing machines, but does it also hold for our toy programming language, for the language while? So if I give you some program in the language that we use at the beginning of this course for defining all sorts of semantics, if I give you a program in the while language, do you think it's undecidable to say whether it terminates? Or do you think that might be decidable? Well, actually, the real point that most of the time is responsible for decidability or undecidability is how much memory the application can use, how much memory the program can use. So if you consider our while programming language, but say that the variables are, for example, 32-bit or 64-bit integers, then the overall number of states that we can have in our program is finite, right? So basically, we can just run the program, and if we saw a state for a second time, we understand that, okay, we are in a loop, and we are in a cycle, and the program never terminates. But if we ran the program and it terminated, then we say, okay, it terminates. But this only works if the domain of all of our variables is finite. The way we defined the while programming language was that actually the variables are real. So I'm thinking of infinite, actually uncountable real numbers, right? In that case, what happens is that you can basically write a while program that models any Turing machine that you want, because you can just use one of the variables as your tape. Okay. So yeah, the undecidability kind of also extends to our language. Okay. So we need to somehow find a relaxed notion of termination, something that is like a special case of termination, so that we can say, okay, even though I cannot solve the general case of termination, I can at least solve this case. And to do that, we will actually need a completely different reformulation of termination. So here's the thing. Let's say that, again, my input was a program P. And also some inputs for P, so some string sigma, right? So what I can do is that I can consider the set of all possible states in the program P. So let's say that S is the set of all states in P. Actually, I'm not going to be very strict about what I mean by a state, because again, at the beginning of this course, we saw that you can define states in many different ways based on how you define your semantics and so on. But basically, let's think of it as the set of all possible configurations of the program. So if your program is a while program, let's say that this is the set of, for example, all pairs of valuations and line numbers. Okay, so every state that your program can be. So based on this, I'm going to define the notion of a ranking function. Okay, and a ranking function is basically a function f that maps our states to, okay, for now, let's say maps them to natural numbers. Okay, so it basically gives a rank to every possible state of the program, such that if I can go from some state S to S prime, so if S prime is a successor of S, actually, maybe it's better not to use this notation. Maybe it's better for me to write if S prime is a successor of S. Then the value of F at S prime is less than its value at S. Okay. So what am I doing? I'm giving a rank or a number to every possible state of my program. But I'm also saying that in every step of execution, if I go from a state S to some other state S prime, then my rank decreases. Okay, so here's the first thing that I want to prove. If a ranking function f exists, then P terminates. And this is basically over every input. So let's say, let's get rid of our input string. And let's say that what we are asking for is whether the program terminates over all inputs. Okay. We can actually model the input by non-determinism as well. So this is not less general than the normal case. So this is the first thing that I want to prove. I want to prove that if I have a ranking function, then my program terminates. Why? Yes, because, well, at every step of the execution, the value of f is decreasing. Let's say that I started at some state S0. So the value of f was a fixed natural number f of S0 at the beginning. And at every step, it's decreasing, and it cannot decrease forever because f maps states into natural numbers, and natural numbers are bounded from below. Right? And because it cannot decrease forever, so it has to end at some point, and that means that the program has to terminate. But what's actually even more interesting is that the other side holds as well. So if P terminates, then a ranking function exists. And for now, let's say that we don't have non-determinism. We will talk about non-determinism later on. For now, let's say that we are in the simple case with no non-determinism. So why is this true? So I have a program P, and my program P always terminates. Why should I have a ranking function? So there is some caveat here, and the caveat is that I have to kind of change the definition of my states, because I can have a program that has an infinite loop, but somehow never gets to that infinite loop, right? So let me write a program here. I can have something like this. If 1 is greater than 2, just go into an infinite loop, right? So this program will not have a ranking function, because you cannot assign a value to the states here, because you come back to the same state over and over, right? But at the same time, the states that cannot be ranked are actually not reachable, because they're inside this if. So let's say that S is the set of all reachable states in P. Okay? So I take the set of all states that can somehow be reached from my initial state. Okay? And then I say that a ranking function is a function that maps each one of these reachable states to a natural number. And it also decreases whenever we execute one step of the program. Okay? The first part holds trivially. But now I want you to prove that if P terminates, then a ranking function exists. So any ideas? Use the execution trace. Well, that actually works if we had only one execution, right? But now the problem that I'm looking at is whether P terminates over all inputs. So the point here is that, okay, let's go back to the definition of S. S is the set of all reachable states in P, right? So for every state in S, there is at least some input such that if I run the program on that input, at some point I will get to this state, right? So when I say that the program should terminate, it means that when I get to this state, if I run the program from this state onwards, it should also terminate, right? So basically what we have to prove is not just that the program terminates starting from the initial state S0, but that it actually has to terminate from every state in S. Right? And actually what helps us with this is, again, the definition of ranking function. So we just showed that if P terminates, then P terminates starting at every reachable state. So P terminates starting at every state S in our set of reachable states. Okay? So I can actually group the states in S based on how many steps it takes from that state to termination. So let's say that S0 is the set of reachable states from which we will terminate in 0 steps. So the program has already terminated. S1 is the set of states from which we will terminate in 1 step. Okay? and I define every other S. So Si is, first of all, a subset of S, because we are only talking about reachable states. And also Si is the set of states such that if we start the program P, set of states, let's call it Si, such that if we start P from Si, we terminate in exactly I steps. Okay. So if I define this Si, I also have the assumption that my program terminates always, right? So how can I write that assumption in terms of Si? It basically means that S is the union of all Si, right? Because at every state in S, I am sure that if I run my program starting from this state, I will terminate in finitely many steps. So if I terminate in n steps, then my current state is in Sn. Okay. So S is the union of all Si. Now I can easily use this to define my ranking function, right? So I define my ranking function f from S to n. Let's say I can also have 0. And the way that I define it is that f of some state S is I, if and only if S is in Si. Right? So the ranking function basically just gives me the number of steps I have to take until termination. And because every time that I go from a state to its successor, I get one step closer to termination, then I have the conditions of the ranking function that basically the value of f decreases in every step of execution. And of course, I can have 0 here, it doesn't matter. The only thing that we need is that it should be bounded from below so that we cannot take infinitely many steps. Okay. So now what do we have? We basically have a completely different definition for termination. Now, instead of asking, given a program, does this program terminate? I can ask you, given a program, does it have a ranking function? But of course, this doesn't change the undecidability, right? So figuring out whether a program has a ranking function is also undecidable because it's equivalent to figuring out whether the program terminates. But it gives us some leeway, and the reason is that basically, instead of asking for any ranking function, now I can look at specific families of ranking functions. I can give you a program and ask, does this program have a linear ranking function? Does this program have a ranking function of a specific form? Right? And then maybe we can solve the problem for these cases. Maybe we can solve the problem for the special cases where the ranking functions have some nice properties. But if you look at the other formulation was, does this program terminate? And we couldn't really find any special cases there. Okay, so let's just do some playing with our ranking functions. So here's an alternative definition of a ranking function. I can say that my function f maps S to this time, let's say R or R plus, or maybe to non-negative reals. Maybe it maps S to 0 to infinity, right? Or maybe it maps S to anything that is bounded from below. So K to infinity, okay? And let's say that if S prime is a successor of S, then f of S prime is less than or equal to f of S minus some epsilon. Okay. These changes don't really change what a ranking function is, right? Because the basic idea behind the ranking function was that you should have some value that is going to decrease. It should be bounded from below, and you shouldn't be able to decrease it forever. So here, instead of having a natural number, you have a real number, but it's bounded from below. And also at every step, you are decreasing it by epsilon, so you cannot decrease it forever. Right? So we can also work with these kinds of ranking functions, which are basically ranking functions that map our states to real numbers. Okay. Now, with these ranking functions, it actually makes sense to now ask, what happens if f is, for example, a linear function in terms of the valuation that I have? Or what happens if f is, let's say, a polynomial function? So here's a simple example. Let's say that I have a program, and the program is very simple. While x is greater than 0, decrease x, and that's it. So let's say I want to prove that this program terminates. What I can do is that I can actually find a ranking function for this program. Now, can you think of a simple ranking function? Well, in order to have a ranking function, we should actually first define what our set of states are. So let's say that I give line numbers. This is line number 1. This is line number 2. And let's say that the set of states is basically tuples or pairs where I have a line number and I also have some value for x. So the line number is either 1 or 2, or maybe I can also add a 3 here, which is where the program terminates. And the value that I give to x, let's call it x bar. The value x bar of x is, let's say, a real number. So this is the set of states that I can have. And all of them are reachable because I don't have any assumption on what the value of x was before here. So I'm not going to talk about reachability. So I want a ranking function for this. Can you just guess the ranking function? So what value do we have here that is decreasing and cannot decrease forever? We have x, right? So we should somehow be able to find our ranking function based on x. So actually, I'm going to do it in a more methodical way. So let's say that at line 1, my ranking function is f1. So, or maybe like this, f of 1 and x bar is, let's say, some constant c0 times x bar plus some other constant c1. Okay. And let's say that my ranking function at line 2 is of this form, c2 x bar plus c3. And let's say that my ranking function at line 3 is also of the same form. Okay. So what do I want to do? I want to find values for C0, C1 to C5, such that this whole thing becomes a ranking function. Okay. But let's actually write the conditions of a ranking function. So our first condition was, let's say we are working with this type of ranking function. So our first condition is that the values should be greater than 0 or greater than or equal to 0. So basically, I should have C0 plus C1 greater than or equal to 0. And this should hold for every valuation. right? Okay, then what? Then I should also have C2 plus C3 greater than 0, and this should also hold for every valuation. And the same thing for my last line. Okay. We also need that our value decreases every time we take a step in the program, right? So when I'm at line 1, what happens? I can either go to line 2 if x is greater than 0, or I can go to line 3 if x is not greater than 0. So what I need is this. For every x, if x is greater than 0, then when I go to line 2, I get what? I get C2x plus C3. This should be less than or equal to what I had before, C0x plus C2 minus some epsilon. Right? And actually, epsilon is also a constant that we have to find a value for. So we have to find values for C0 to C5 and also for epsilon. Okay, similarly, if I'm at line 1 and the while condition does not hold, I will go to line 3. So if the while condition does not hold, then I go to line 3 and the value that I have there is C4 x bar plus C5. And it should be less than or equal to the value that I had at line 1, which was C0 x bar plus C1. And of course, we have minus epsilon. Okay, so these are the transitions that go out of line 1. Actually, I can draw all the transitions. So I have a transition here, here, and then from 2, I can only go back to 1. Okay. So what happens in line 2? If I'm at line 2 right now, I will decrease the value of x by 1, and I will then go back to line 1, right? So, and there is no condition like this, because anyway, I will do that. So when I go back to line 1, what is my value? My value is C0x plus C1, but it's the new value of x, which is 1 less than before. So it's actually C0 x bar minus 1 plus C1. And this should be less than the value that I had at line 2, which was C2 x bar plus C3. Okay, and also, as always, I need minus epsilon. So this is the problem that I have. I have these constraints here, and I want to find values for C0, C1 to C5, and also for epsilon, such that all of these constraints hold. But actually, is that possible? So can I find values for C0 to C5 and also for epsilon? And of course, epsilon should be greater than 0, such that all of these constraints hold, such that f becomes a ranking function and proves that my program terminates. Well, let's see what happens. Here, I should have C0 x plus C1 greater than or equal to 0, and this should hold for every value of x. So the only way I can do this is if C0 is 0, and if C1 is a positive or non-negative constant, right? And then the same thing happens here and here. So all of these have to be 0. So C0, C2, and C4 have to be 0. But if all of them are 0, then what problem do I have? Well, basically my ranking function does not depend on X at all. It's only a constant number at every line. And it's really easy to see that we cannot have that kind of ranking function. Okay, so in other words, the constraints that we wrote here are actually unsatisfiable. But what does this tell us, that these constraints are unsatisfiable? What it tells us is that we cannot have a ranking function of this specific form. We cannot have a linear ranking function, right? But if we change the form, for example, if I say, okay, I want a ranking function that is quadratic. So if I can have another term here that is, for example, some other constant times x bar squared, then it might become solvable. Another way that we can make it solvable is if we can restrict the set of reachable states. So if we can have some sort of an assumption on what kind of states are reachable, right? So for example, if I have an assumption here that x is at most 100 at this point of the code, right? What does this assumption do? It basically limits my set S of reachable states. It says that at the beginning, when we are starting our program, the value of x is bounded. It's at most 100. Okay. Then what happens? Then the thing that happens is that, well, at this line, now I know that x is at most 100. So I can say that if x was at most 100, then this whole thing should hold. Right? So we call these assumptions invariants. An invariant is basically an upper bound on the set of states that are reachable at every point in the program. So this invariant here is telling me that at point 1 of your program, all the values that are reachable have their x be less than or equal to 100. Okay, and actually invariant generation is one of the topics that we will cover in the coming sessions. So for now, what we're going to do is that we're going to change our perspective, and let's say that instead of just having a program and being asked, does this program terminate? We are given a program and we are also given invariants at every point of the program. So I have an invariant x less than or equal to 100 here. What invariant do I have here at line 2? So I know that x is at most 100 at line 1, but I have entered line 2, which means that x was greater than 0. Right? So at this point, I know that x is greater than 0, and also it's less than or equal to 100. Okay. What do I know at line 3 when the program has ended? Well, x was initially less than 100. And it was never increased, right? So x remains less than or equal to 100 here. But I can do even better. So if I've reached line 3, this means that at some point I was at line 1 and the while condition did not hold. And that was why I went to line 3. So at this point, this means that x was less than or equal to 0, right? Otherwise, I wouldn't be at line 3 at all. So these are the invariants that I have. I wrote these invariants manually right now. I just assumed the first one and computed the other ones manually. But in the next sessions, we will see some automated ways for actually generating these invariants. But now that I have these invariants, I can actually add them here as preconditions. So when should this ranking function be non-negative? It should only be non-negative when we are in a state that satisfies this invariant. So only if our x bar is less than or equal to 100 should I have this. Okay. Similarly here, I can add the invariant, this one. So let me call this I1, I2, and I3. So here, if I2, then this. Here I will have if I3, then this. So basically, the value of the ranking function should be non-negative only in the reachable states. And the invariants are giving me an over approximation of my reachable states. So I can say that the value should only be non-negative when the invariants are satisfied. And the same thing also here. So here I can say if I1 holds and also this holds here as well. And here I can say if I2 holds and this holds then. Okay. So now do we have an answer? Can we find C0 to C5 and also some epsilon such that all these constraints hold? So any ideas? We still kind of have the problem that we had before, right? So here we're saying that whenever x is at most 100, we should have C0 x4 plus C1 greater than or equal to 0, right? So this can only happen if I have a negative C0, right? Because it has to hold for every x. But then if I put a negative C0 here, I can make this positive, but then the whole thing really crashes. You can't, I don't think you can find an answer here. Okay, I'm not completely sure, but I cannot immediately see an answer. So sometimes what happens is that we have invariants, like this case, and we write these constraints and still we see that we don't have an answer. And I'm not completely sure that we don't have an answer, but at least I can't find it. Okay. In these cases, usually what we have to do is we have to go back to our invariants and find better invariants. Okay. Or we have to, again, compromise less on the form here, and let's say that it's quadratic or it's some other function. But one thing that I can definitely do right now for this example is just say that x is also greater than or equal to 0. Sorry for writing so many things like that. So if x is between 0 and 100 here, I know that x is greater than 0 and less than or equal to 100 here. And what do I know here? I know that x is less than or equal to 0, but I also know that it is at most how much? So I know that x is greater than -1, right? Because even if x is 0.1 here, then I will get one deduction here and come back. So here I can say x is less than 0 and x is greater than -1. Okay. Now with these invariants, and basically putting this here, with these invariants, do I have an answer finally? Can you give me a ranking function with these invariants? So give me values for C0 to C5 and also for epsilon such that this whole thing holds. Well, here's the thing, X is decreasing, right? And how many steps does it take for it to decrease by 1 unit? It takes roughly 2 steps, right? Going from 1 to 2 and back and so on. So what I start with is that I can say, okay, f of 1x bar, let this just be 2x. Okay. And then f of 2x bar can be 2x minus 1. 2x bar, sorry. So x is the variable and x bar is the value of x. Okay, if I have this, then which conditions are satisfied and which are not? So this one's definitely satisfied, right? And I can just put epsilon equal to 1. So this is satisfied because when we go from line 1 to line 2, our value decreases by at least 1, which is what this condition says. What happens when we go from line 1 to line 3, where our value should also decrease by at least 1, right? So we haven't defined f at point 3 yet. Let's say that f of 3x bar is just 0 always. So what I want is that whenever I go from 1 to 3, my value should decrease by at least 1. So instead of just having 2x bar here, I can have like 2x bar plus 1. Because at point 1, I know that my x is between 0 and 100. So if I have this, when I go here, I know that my value decreases by at least 1, but I should also add this here. So get rid of this whole thing. So if I have this function, is it a ranking function? Let's see. So our values should always be non-negative. At point 3, it's definitely non-negative. At point 2, our x is between 0 and 100. So this is non-negative. At point 1, it's also non-negative. In every transition, our value should decrease by epsilon, which is 1 at the moment. So if I go from line 1 to line 2, which is here, my value decreases by at least 1 unit. That's fine. If I go from line 1 to line 3, which is this one, my value was at least 1 at the beginning because x is non-negative, and now it has become 0. So it has decreased by 1. And what happens when I go from 2 back to 1? Well, x is decreased by 1. So now I have 2 times x minus 1 plus 1, which is less than 2 times x, which I had before. So this is a ranking function. So because we have this ranking function, then we know that this program terminates. We saw a bunch of ideas here. The first idea was that if you don't have invariants, you really don't have much of a chance in finding ranking functions. Because without invariants, we couldn't even find a linear ranking function for this one. The other idea that we saw was that we can actually fix some sort of template for a ranking function, for example, this template that I fixed here, and then try to synthesize values for these coefficients in our templates, right? And here I fixed a linear template. I could have fixed a completely different template. I could have fixed an exponential template, whatever. But we're going to keep to the linear case for now. Okay. So when I fixed the template, I could basically reduce my problem to this problem, which is a constraint solving problem. And then I solve these constraints manually. But if you have, for example, an SMT solver, you can just give this constraint to the SMT solver and it solves it for you, right? So we have at least some sort of an automated method for figuring out if we have this kind of linear ranking functions, right? We write these constraints and then give them to a solver. The problem is that we don't really have a sound, complete, and terminating solver. So we have to find a better way of actually solving these kinds of constraints. And that's what I'm going to talk about right now. Okay, So just for the sake of argument, let's say that my functions are, my ranking function is basically linear at every line of the program. And let's also assume that the program itself only has linear conditions and linear assignments. Because I want to be able to talk only about linear expressions in the rest of this session. Okay, so we started from the general halting problem, and we first reformulated it as the problem of finding a ranking function. Now we are looking into special cases. What are the special cases? Well, we are limiting the set of programs. We are saying, okay, let's only look at the programs that have linear constraints and linear assignments. And we are also limiting the set of ranking functions. We are saying, okay, let's only look into the ranking functions that are linear at every line of code. And on top of all of these, we are also assuming that we are given some invariants. And let's also assume that the invariants are also linear. Okay, so we are making so many different assumptions, really focusing on the most linear case of termination. And we want to see if we can actually decide this problem. Okay. So in the linear world that we are in, we have to basically solve a bunch of constraints that are like this. So I'm going to write actually the general form of the constraints that we are trying to solve. So let's say that the set of variables in my program is v1, v2 to vr. So in that example, I had only one variable x, right? So what format do these constraints have? They all have this universal quantification over valuations, right? So they should all hold for every value of the program variables. Actually, it's useful to think about the types of variables that we have. We have two different types of variables. We have program variables, which are variables that are in my program. And we also have these coefficient variables, which are the variables that I decided to put there for finding a ranking function. And I also think of epsilon as a coefficient variable. Okay, so I have two types of variables. I have program variables, I have coefficient variables. What do I want to do? I want to find values for coefficient variables such that they form a ranking function. What does that mean? That means that I want to find values for these coefficient variables such that these constraints hold. And these constraints all quantify over my program variables. Okay, so let's say that let's say my set of valuations is v1 to vr. And let's say that the lines in my program are lines 1 to n. Okay, so what was evaluation? Evaluation was basically a function that maps every program variable to its value, right? So my set of states would be the set of pairs of lines and valuations, right? Where L is a line of code, and my valuation is basically a function, right? And other than this, I also have a bunch of invariants, right? I have I1, I2 to IN. These are my invariants. Now, what are the conditions for a ranking function? Again, we just follow the definition. So the definition of a ranking function was that it has to be non-negative at all times. So at every line of code, for every L, I should have this. I have to say that for every valuation, if the valuation satisfies my invariant at that point of program, then f of that valuation should be should be greater than or equal to 0. Right? And also for every transition, I have some constraints like this. So let's say that I have a transition from line L of my program to line L prime of my program. Okay. And let's say that this transition has some condition phi. So for example, it only happens if at line L phi is satisfied. For example, if line L has an if condition. And let's say that it also has some update function u, which updates the value of the program variables. So for every transition of this form, I have to say that the value of my ranking function f decreases. So I should have for every valuation, if the valuation satisfies the invariant at point L, and if it also satisfies this phi, then, well, when I go here, the value that I have here should be less than or equal to the value that I had originally, which was f of val minus some epsilon, right? But when I go to L prime, what is my value? My value is f of u of val, because the valuation is now updated by this function u. And actually, I'm going to add these indices for f. So this valuation is at 9L, this valuation is at 9L prime, this valuation is at 9L. Okay. So again, just like before, what I do is that I set up some template. I say that, okay, let's say that f1 of a valuation, which is basically f of 1 and that valuation, is of this specific form. It's C0 plus C1 V1 plus C2 V2, so on to CR VR, where this bar basically means the value. So okay, so this is nothing more than what I have here. So at every line of code, I have a template like this that basically tells me how my rank how my ranking function should look like. Okay. So yeah, I have, this is for line 1, but I have the same thing for every line of code. And I also have these constraints. So I want to basically solve for these constraints and find the value for epsilon, and also find the value for the CIs. Now, if we look at the constraints that we have, they're actually all of a very nice form. All of them are of this form. For every valuation, if some constraints A hold, then I want some other constraints B to also hold. And A and B are sets of linear constraints or linear inequalities. Right? So for example, here, what I'm saying is that if the linear inequalities in the invariant hold, then I want also to have this linear inequality. I want to have my ranking function be non-negative. Here, what I say is that if the invariant holds, which is a bunch of linear inequalities, and if also the condition for transition holds, which is another linear inequality, then I want to have this linear inequality as well. Okay? So all of my constraints are of this form. All of my constraints say that for every valuation, if a bunch of linear inequalities, which I call A, hold, then I should have another bunch of linear inequalities, which are B, to hold as well. Okay. So actually, I can break this down, right? So I can write it like, okay, I can write it in a more linear algebra kind of way. I can say for every vector valuation, if A, so I can think of A as just a matrix. If A times this valuation is greater than or equal to some other vector, so let's call it C, then I should have also B times this valuation greater than or equal to some D. Right? So what I'm doing here is that I'm saying this was a set of linear inequalities. So I can write a set of linear inequalities as a matrix times my valuation as a vector. And I can say that these are greater than or equal to some other vector. Right? So this comparison is applied in a component by component basis. And on this other side, if I have more than one linear inequality, I can just write more constraints and make it so that I have only one at the right side of every constraint. And then I can write that one linear inequality in this format, basically some vector B, again, times my valuations is greater than or equal to some, this is now a scalar D. Okay? So this is what I want to solve. How can we solve this? Well, basically, the question that we have is pretty much a linear algebra question. The problem that we have is that we have a bunch of linear inequalities on the one side, and we want to see whether these linear inequalities actually lead to some other linear inequality. So do we have this entailment or not? If I have these linear inequalities, can I deduce that I have this linear inequality as well? Okay. And this is something that we usually solve using a theorem in linear algebra, which is called Farkas lemma. Okay. So what's Farkas lemma? This is actually the main tool that they use for solving these kinds of inequalities. And quite simply, I can write it like this. I can say that, let's say I have a set of linear inequalities. So let's say that I have, first of all, a set of variables, which is V1 to Vr. And I also have a set of linear inequalities, a system of linear inequalities over these variables. And let's say that these linear inequalities are of this form. So C0, 0 plus C0, 1, V1, so on to C0, R, VR is greater than 0. C1, 0, C1, 1, V1, C1, R, VR is greater than 0. And let's say that I have M of these. Okay. So I have a set of variables, V1 to VR, and then I have M different linear inequalities over these VRs. Okay, and let me call these inequalities, whatever, let's call them psi. Okay, and let's say that I have another inequality, which I call phi. And let's say that phi is of the form D00 plus D01 V1, so on to D0R VR is greater than. Okay. So I have a bunch of linear inequalities and I have one extra linear inequality. And my question is this linear inequality, is phi entailed by this system? So my question is, does my system psi entail my new formula phi? And this is what I want to solve using this Farkas lemma. So we're running almost out of time, but I'm just going to tell you what this Farkas lemma is, and then we will cover the rest of its applications to program analysis in the next session. So if you know these inequalities, if you can assume these inequalities, what other inequalities do they entail? So how can you obtain new inequalities from a bunch of assumed linear inequalities? Well, one simple thing that you can do is that you can, for example, add two of these, right? So if I'm assuming that this linear inequality holds and this one holds, then I can just add them together and that one should also hold. I can actually do better than that. I can basically first multiply each one of them by a non-negative constant, and after that, add them together. Right? So if I know that all of these linear expressions are non-negative, what I'm saying is that basically I know that any non-negative combination of non-negative expressions is also non-negative. Right? But, well, what else do I know? I also always know one trivial inequality, and that's that basically 1 is greater than or equal to 0. Right? So I can add this trivial inequality to my set, and I can say that, okay, instead of just looking into non-negative combinations of my original inequalities, I can look at non-negative combinations of my original inequalities and also this trivial inequality. Okay, so everything that I obtain using this method is definitely non-negative. But what Farkas lemma says is that the other side holds as well. So if these inequalities entail this one, then the entailed inequality phi should definitely be writable as a non-negative combination of the original inequalities and also of 1 greater than 0. Okay, does that make sense? So it's a very famous theorem in linear algebra, basically. So now we are out of time, and I will continue with this tomorrow. Sorry, in the next session. But the only thing that I want to say is that now we have all the ingredients for actually finding linear ranking functions, right? Because with a linear ranking function, I start here, right? And then I write these inequalities. And all of these constraints that I have here were of this form, that if a bunch of inequalities hold, then some other inequality should hold, right? And I didn't know how to solve this, but then Farkas lemma says that I can solve this if and only if the inequality on the right-hand side is a non-negative combination of the inequalities on the left-hand side and also the trivial inequality, right? So based on this, I will get a sound and complete algorithm, but that's something that we will consider in the next session. Okay, so are there any questions? Okay, great. So I stopped the recording.